Definite integral, we can write that up till now we've been talking about an indefinite form of integral that has an expression of what we call the arbitrary constant. But in case of definite integral, we can put this down for understanding's sake that definite integral are those that are formed by integrating as now we've discussed about integration and we call it summing up, integrating an integrand with a specified limit, So when we talk about definite integrand, students need to keep this in mind that we are not applying any form of limit because we are of constant because they are limit of values. So now whenever you are dealing with definite integral, you have to have it at the back of your mind that you have an absolute value. So we can always write that result, that is another very good important things you can keep in mind. Result will be an absolute, that is an exact value, an absolute value. Excuse me, so please note that absolute value. That is, you are going to have a definite answer to them. So whenever you are trying to integrate a sort of integral with respect to limit, this is what we call a definite form of integral. We have quite an example of this, and when we talk about limit, like I said, you are integrating with a specified limit. Limits can be classified into two categories. Students can also keep that in mind. It's very, very important. You can also classify limits into two categories. You have limits can be in terms of what we call upper limits, and the other one we call the lower limit. So you need to keep this in mind as we are going to do some example. The essence of this is to get everything we need in our physics, but I also see that this is so important in our mathematics. I am doing this calculus because of the physics A-level student, and I also see this as part of things that you guys need in your mathematics. So we can talk about next thing, which I think is important, is methods that we use for integrating or let's say the procedures, anyhow you want to call it. You can call it method of the procedures of limit. So now what we do here is let's take a very simple example for understanding's sake. Maybe we have a situation whereby the standard definition we can give to you, we have an integrand from limit of a to b of f prime of x. So here, what we have written here, under here, is called, this place is called the lower limit, and this place is called the upper limit. Sometimes you see it, we call it in mathematics, sometimes it is called ordinate. So sometimes you might see it as coordinate. So we still mean upper and lower ordinates. We're still talking about the same thing. So now everybody knows now that if we integrate f prime of x, so far we say integration is summing up, you can say integrating f prime of x, definitely we are going to get f of x. As integrating f prime of x will give us f of x, and we are now taking limit of f of x from b to it. So what we do is that from a to b, what we do is that we are now going to have something like substituting the value of x value for a and b, but we always subtract the upper ordinate or limit from the lower ordinate. So this is the way we actualize this, and this is the standard definition we give to a limit of a function of a definite integral. So I know many of you might have learned this in your early classes. So now we can take an example for understanding's sake, and let's take some basic example before we talk about some little bit of advance. So examples are just for us to understand the basic concept. So we say we have let's take a very simple one. First, we have 1 integrand of we have 0 to pi by 2. We have to do what we call cos x dx. So now, so far you can see we have limit of function. So this type of integration does not have the constant. So what you just do is just you integrate this, already discussed. Cos x is going to give us sin x. Then you are taking the ordinate from 0 to pi by 2. So what this simply means is that you substitute x value when it is 0, when it is pi by 2, that is upper minus lower, as you can see here. So we say here, to be time pi by 2, x is now pi by 2. We have that. I believe students to remember all this stuff. Sin pi by 2 minus sin 0. So and sin pi by 2 from a calculator is going to give you nothing but sin 90. Sin 90 is 1. A pi is a radian, which is 180 degrees. And sin 0 is also 0. Answer to this will be 1. That is the answer for your question. So as you can see, answer that we are deriving from this is giving us an absolute value. We have an exact value. Unlike the other one, the answer always being in terms of a. You can take up one more. So let's take another one. We say 2. And also take an algebra form of function. Let's take an easy question for understanding sake, because we still have a long way to go. We are trying to do s cubed dx, integrating that from limit of 2 to 3. So here, the same process is what we're going to do here. We are trying to integrate this. We know that it's going to give us x4 over 4. So we are taking the limit from 2 to 3. I hope students still remember all this stuff. So here, from here, we just do direct substitution of upper ordinate minus lower ordinate. If you like, we say upper limit minus lower limit. So from here, you have to say this is our 3 to the power of 4. I'm substituting directly. Then I'm going to have 81 over 4 minus, you can see 2 now. 2 to the power of 4 is 16. 16 over 4 is 4. So if you do this, I think your answer, you can go by your FCM. So FCM will be 4. 81 minus 16. And that should give you 65 by 4. So that is the answer to that. And you can see from what I've said that all answers are going to give you an absolute value. And that is why you call them a definite form of integer. So students should keep these short things in mind, because these are the basis of ordinates and limits of definite integer. So again, we can also discuss about another important concept about application of definite integral, which I think we are also going to need in our physics class, and we are also going to be needing it in our mathematics class. For that, we can quickly talk about what we call the calculation of area under curve. Let's start that. Area under curve. So it's one of the application of definite integral, which I believe we might have studied in our early classes. So to carefully analyze that, let me give us a graph in the xy plane and use that graph to explain as usual and way to make sure you all understand the concept very well. So let's say we have xy plane and we have a curve as usual in the xy plane. It is moving in that manner. So we have a curve like this, and inside the curve we have different points. Now let me just indicate 2 points. I have these I'm taking as point y, and the other I will take as point x, trying to make it a little bit clear. So I want to take the limit of the point from this point to this point. I will call this x1, and the other one I'm going to call this x1. This is x-axis, everybody knows that. And this is y-axis. So I'm going to call this point x1 and this point x2. So not to waste time for you to see clearly, I will soon move to the next slide. Now what we are trying to do here is to understand that this is a curve. Now if I am asked to find the area of this curve on a normal day, I cannot actually give the definition to the shape of this curve. So we use the application of definite integral to actually derive formula or application to calculate the area under this curve. Now, to do that, what we do is we just take a particular position from the what? From this point, we can call it an elemental change. We can say from y now, we are taking a shift of x. Here now, I'm taking an elemental position. Let me just take a small area at this point and at this point. I just want us to understand the concept first before we go into examples. Now, what I've done here, if you watch carefully, is that I'm taking two different points, which is an elemental point, that is a small variation under this curve, and I'm taking that first one as x, and the second one as it has changed from x to a point of dx, or as you can see, it's just a small change. Here at this point now, I can say, if we are measuring this particular point with respect to the same height, as you can see, we can actually trace the y values, that is at different values. We can also have the y values of this point. So what I'm trying to say here is that to get the area of this simple or elemental curve that I've actually carved out from this, I can go by saying, you can see it's having the same height. So I can say, because it's forming something like a rectangle, if you can see the shape very well. So from what we've learned in early classes, I can now say the change in the area of this one, I can say the elemental area, I will call that the A, is now equals to a rectangle area from any classes. It's just y, which is what? The length, times the breadth. The breadth here is changing from x to dx. So I'll call that what? Dx. I'll be changing x, we call dx. That's like saying length times breadth. I hope students are following this. Now, that is just the elemental area of the part I have actually brought out. So this is just elemental area. Now, having gotten that, to now get the total area of this whole shape, I will now say, okay, I am taking the point from the point of the beginning, the point of the curve here should have been at this beginning of this thing. Well, it doesn't mean. But if I'm looking for the area under this, which is all the total area here, as student can see, from x1 to x2, I will now say, because I am taking the value of this is also x1 from this point to this point, as you can see, I can now say the area of the whole shape. So area of the curve can now be given as, because see, I am just taking it now from the point of x1 to x2. So area of the curve will now be equals to, we are taking the total area of the elemental shape. Now is now the same thing as integration of the area of the elemental strip, which I have actually carved out here, which I call dA. But this time, I am taking the limit from the beginning of the curve towards the x-axis to the end of the curve, because I am taking the limit from x1 to x2. So this is the application that we use, which you can now write in this as integration of, what is the A? The A is y dx, taking the limit from x1 to x2. So this particular formula is the simplest formula we use in mathematics and physics to actually estimate the area of random figure. By taking an elemental area, we now move it to the particular area that we want to calculate. I hope students are good with this one. And to understand this very well, we can take an example for quick understanding. So about that, let's take an example, which I think is going to help us in understanding this very well. So going to do, let's go to the next slide to quickly understand very well. So let's take one more. Let's take an example on that. So now we are there. Very good. So examples now. Let's take just a simple example. From one example, you can do other examples, and I believe definitely you are going to get it. So taking an example here, we take our example we have here is a find. Let's take, this is a popular mathematics question you see in your post-UTME and in your JUPEP exam. Find the area between curves. Curve y is equals to x squared plus 7x plus 3. Between curve y equals to x squared plus 7x plus 3 and x-axis, here between the curve and the x-axis, from x is equals to 0 and x is equals to 2. So far we have studied days. To solve this one directly, guys, we don't need to waste our time. So we already know from the concept explanation now, our area between curve is always giving us integration of the limit. The limit here is from 0 to 2, lower limit to upper limit. Then we have y dx. So this is what we use. And you just substitute directly as you are given the value of y as x squared plus 7x plus 3 from 0 to 2. This will be the area of the curve. And you know you can integrate this directly. I hope students to remember that to avoid error. So it will give us answer now. Will now be integrating this. This is x cubed. We've done all this by 3. Then we have a plus 7x squared over 2. Then we have a plus 3x. So because we are dealing with definite integral, we are taking limits from 0 to 2. So what you substitute is upper ordinate minus lower one. As you can see, if you put 0 in this expression, everything here will be 0. So let's do this one. This will be 2 raised to power 3. This is 8 by 3, or 8 over 3 if you like it. This is plus 14. This is 2 squares are 4. So 4, 2, that's 14. You can always ask me. Then this one is a plus 3x. This is 3. So 3 times 2 are 6. So minus lower ordinate is 0. Everything here will be 0. I hope students are following. So from here, we can say the final answer to this will now be equals to, from here, we can do this 8 over 3 plus 20. Without wasting time, this will give us 68 over 3. And that will be the question. So you can always have it at the back of your mind that directly when you are looking for area between curve, use the direct formula, then you take the limit of the function from lower to higher limit, and you get what the direct answer. So now we still need to talk about one more thing before we call it a day on this slide. We can also talk about the other application of definite integral, as we can use it to calculate area of different geometric shape. So I'll be talking about this because this is the most important, because in our physics, we are going to be talking extensively on derivation of formulas and as well as some important shapes which you need to always keep in mind. So it is very, very important to understand how to use integration to get the area of different shape. To start with, I will start with a basic one. Let's take, I'll only do one here, maybe in the next slide. I'm going to discuss more about other things. We can take the first one. I'll take a square or a rectangle. Let's do the area of a rectangle first. Let's take a rectangle. And let's try to use using integration now. So we want to use integration to find the area of a rectangle. Now, here, this is what we do, dear students. We have a rectangle in front of us. We want to calculate the area. As I have discussed, we know a rectangle basically has a formula of length times breadth. I hope students still remember that. So what I will do here, my dear student, as usual, is to take an elemental part from what? From this particular thing. I can just take, you know what I mean by elemental part, just a small part or a strip. So we take it like this. So I just want to consider the two elemental strip there, as you can see there. So I'm taking those elemental parts. So I'm taking this, let me just, which I will call, as you know, we are taking it from the beginning to the point of here, which is definitely on the x-axis as discussed in the other one. So the elemental distance here, I call it the x, as you can see. So I will now take the limit of the function. We can just write, for understanding's sake, area of elemental strip. As you can see, I can say area of a rectangle is always length times breadth. Now area is changing from A to the A, just like what I did there. Then it will now be the breadth. You can see from here to here, multiplied by, I'm taking the area of this from this point to this point. So it's changing from x to the x, you remember? So which I always take as b multiplied by the x. I hope students are still following this. Now, so definitely, if I now need the total area of the rectangle, we can now say the total area of rectangle will now be equals to, just like, because now I'm now taking the whole length from, you can see, I'm now taking it from the point of initial, you can see, from this particular point to this particular point now. So I'm taking it from the point of, let's say, is 0, which is at rest, to the total distance from here to here, which we call what? L. So it is just for me to now classify everything. The former one was just from here to here. Now it will now be integration. Area will now be integration of the area I have here, taking the limit from E0, as you can see, to what? To L. So, and the here, we've already written this. It will now be integration, the here, which is P dx, taking the limit from 0 to L. So now, if we do this, as I believe all students can do this, we can see that because B is not needed in the integration, so integrating this, we say A will now be equals to, you can bring B outside, you have, because B is a constant here, so you are integrating X because you are taking the distance of this X to the X. So here, I will now say, integrating the X, everybody knows I'm going to have X. So I'm going to have X if I integrate, taking from 0 to L, dx. So if I integrate the x, I'm going to have, I hope students understand this, I'm going to have a b open bracket x. I am taking the limit from a 0 to L. You don't need to get bored, because this is just the beginning, and this is kind of very easy. We are going to be following the same processes for all of this. So now finishing this now, dear student, now integrating this, now we have b, as you can see. Now when s is 0, it will be 0. And when s is L, I hope students understand that it will be L. So you have a B times L. So, and that is, everybody knows that area of a rectangle is always breadth times length, or length times breadth. And that is how we come about. You can also take another one, but I think because of time and being signal, we can stop here. In the next slide, we are going to discuss about some other important one, like circle. We talk about cone. And if time permits, I'm still going to talk about a sphere, because we need an elemental sphere in physics. We need a cone in physics, as we are going to be taking elemental change in a value and the extended body of cone, circle, sphere in gravitational force on the physics. So guys, see you guys soon. Don't forget to subscribe to the channel. And if you have doubt, do comment in the comment section.